Standing waves are a neat concept in waves because they bring in together so many things. We have waves that are reflecting off an end, interfering with themselves. If they have the right wavelength, then they're going to make a cool static or standing wave pattern, which ties in the idea of resonance. If you were to shake a slinky or a skipping rope or something, if you were to shake the end up and down, kind of slowly, you're going to get what I would call this first one, the skipping rope kind of idea. That one's called the fundamental, or the first harmonic. It's got a great big long wavelength. Only half of the wavelength fits in the length of the slinky. If you were to vibrate it up and down a little bit quicker, it'll go all gobbly-goopy. There'll be a node that kind of moves around, but at just the right frequency, which corresponds to a smaller wavelength compared to the last one, you'll get this nice static pattern again. It's got one node in the middle. It's got two antinodes. The name of this one is the first overtone or second harmonic. Again, if you shake with a little bit faster frequency, as you shake it with a higher frequency, the wavelength will shrink down. It'll go kind of all gobbly-goopy. The nodes will move around. But then at just the right frequency, which corresponds to just the right wavelength, you're going to get another static pattern. This particular one, the next one, has two nodes. We call it the second overtone. It's got three antinodes. We call that the third harmonic. If you can get the naming down pat, then it's just logic to sort of figure out how these things work. As an example, suppose we have a slinky stretched out and I tell you it's vibrating at the fifth overtone. The memory trick I use is the word Noah. From the word Noah, the fact that it's fifth overtone starting with N, that means there's five nodes. Then I just have to remember that the ends don't count. So I've got the end of a string, one node, two node, three node, four node, five nodes. That's the fifth overtone, so five nodes, and the other end of the string, or slinky. The standing wave kind of fits into that, so it kind of swoops through. There we go. It reflects back on itself, so the entire standing wave kind of looks like this. The way this particular example is worded, it says a wavelength is 3 meters. From what we've talked about, from some kind of logic, we know that a wavelength is two of the football shapes. So that would be one wavelength, that would be a second wavelength, that would be a third wavelength. So the length of my slinky is 3 times the wavelength. In this case, the 3 times the 3 meters means my slinky is 9 meters long. So without any equation, just some common sense off the name, I'm able to draw the picture, and from the picture I can solve the question.